Okay, so hello and welcome everyone to week 2 of interactive live sessions for the course on fundamentals of heat transfer offered by NPTEL. The course is being instructed by Professor Amaresh Dalal from Indian Institute of Technology, Guwahati, Department of Mechanical Engineering, and I'm a PMRF scholar at IIT Madras, and I'll be the TA, and we shall be solving tutorial problems together and discussing the course material and any doubts whatsoever. These are interactive live sessions. Let's keep these sessions as much, interactive as possible. So, with that, let us begin. We will start with question number 1 of today's session. So let's first discuss how we are going to do things. I have polls ready. I can share them, but since there are not many people, we can, I guess, work along with the chat box as well. So once you have found out the solutions for each question, you can type in your answer in the chat box. And after that, we will have a short discussion on the solution. Okay. So with that background, let us begin. This is question number 1 of today's session. Uh, I'll read it out. So Reynolds transport theorem formulation or Reynolds transport formulation relates the control system approach and control volume approach. So is this statement regarding the Reynolds transport formulation or the Reynolds transport theorem uh, is whether true or false?
True.
You can type it in the chat box and we can have a discussion later on. Unmuting and telling the answers each and every time might create a problem if there are many people. Okay, so we have one response and that is true. Okay, so let's have a look at the correct answer. And the correct answer is indeed true. So Reynolds transport theorem, what it does is it basically relates a control system to a control volume approach of the same system. So basically all the laws of nature that we know, be it Newton's law of motion or any other laws, most of the laws are actually known and well understood for control systems. But if you're dealing with fluid flow systems, then a control volume system makes that problem more amenable. But the laws of nature are not known for control volume systems uh, in the same, what can I say, in the same as much readily available as control systems. So in order to connect those and apply the laws of physics to control volumes, Reynolds transport theorem becomes indispensable. Okay, so at any point, if you have any questions, please unmute and ask. Otherwise, we will keep on moving to the next questions. So right now, we will move on to question number 2 of today's session. It says hydrodynamic boundary layer thickness is much smaller than length of the flat plate for high Reynolds number flow. Is this statement true or is it false? So for flow over a flat plate with sufficiently high Reynolds number, uh, is the hydrodynamic boundary layer thickness is it much smaller than the length of the flat plate? Okay, so now also we have one response and that says true. We will wait for other responses as well. Okay, so if there are no other responses, we will have a look at the solution. And here also, this statement is basically true. So what happens is, if I take a flat plate and there is some flow over it, then this boundary layer forms. But however, if the length of this flat plate is of the order L, uh, so if the length of this flat plate is of the order L and the thickness of this boundary layer is of the order delta, then delta is always much lesser than the length scale of the flat plate. So this is what happens, and this is also what we assume for further analysis of boundary layer theory. Okay, so moving on, we move on to question number 3. This says that which of the following boundary conditions is not valid for laminar boundary layer flow over a flat plate along the x-axis. So basically we take the same kind of situation which we saw earlier. There is a flat plate and there is a flow over it. We will assume uniform incoming flow initially, and then a boundary layer developing as it comes in contact with the flat plate. And here definitely we will have, here we will have velocity distribution developing like this. So here we have the y-axis, and in the x-axis we are basically plotting u. So u starts out from 0 and then gradually increases and becomes u infinity within the hydrodynamic boundary layer. So keeping this in mind, there are 4 options given, and we have to find out which one is not valid for laminar boundary layers. So the first option says at y equal to delta. So I have to mention that this thickness of the boundary layer, this is equal to delta at any given x. So we have to find out, we have to determine which of these statements are correct or incorrect. So at y equal to delta, u equal to u infinity is the option A. Option B says at y equal to delta, dou u dou y becomes 0. And option C says at y equal to delta, dou 2u dou y2 becomes 0. Or option D says none of these. Okay, so we have one response, and that's in favor of option C, which says that at y equal to delta, dou 2u dou y2 becomes 0. But if we look at the solution, it's actually none, because that's also what is true. If we have a look here, so at y equal to delta, that is at this location, this is where we are focusing, u becomes u infinity. Further, there is no change in u, so dou 2y, that is equal to 0. And if we take another derivative of it, dou 2u dou y2, this also becomes 0 naturally, because this is nothing but dou y of dou u dou y, and this we already know to be 0. So the second derivative also essentially becomes 0. Is that clear?
Yes.
So that is why the correct answer would be option D, none. So basically all the 3 options, option A, B and C, they are correct. They are valid for laminar boundary layers. Now we'll move on to question number 4. So question number 4 is again a theoretical type question.
Debjit sir, just
Yeah,
one minute.
yeah, sure. Please go ahead.
Okay, we are discussing this earlier question related with the laminar boundary layer.
Correct.
Now my question is, if the same question is asked for turbulent boundary layer, then what will be the answer?
Uh, then also it would be the same, because even if, okay, let me go back. If it's a turbulent boundary layer, then everything else remains more or less same, but the profile becomes a bit like this. This variation is a bit different, but anyway, there are some complexities in turbulent flow on top of what happens in laminar flow. Due to that, there will be some disturbances over there. But if we take a a time averaged version of it, then all the other assumptions, they would be valid for turbulent boundary layers as well. But keeping in mind that turbulence means there will be some inherent unsteadiness and stochasticity to that problem. Could I answer your question?
Yes, yes.
Okay. So moving on, question number 4. Which of the following condition is required for the formation of thermal boundary layer? Is it option A, slender body without flow separation? Option B, high Reynolds number? Option B, high Prandtl number? Or is it option D, all of the above? So these are certain conditions which are required for the formation of thermal boundary layer. You have to pick out which one of the options is correct.
Sir, slide.
Hello?
I am not seeing your slide, sir.
You're not able to view the slides, but I guess the slides are visible. Others can see, right?
Yes, yes.
So I guess it's a problem on your part. I'm seeing that you are, rejoining time and again. Is it still not visible?
Yes, sir, not visible.
Not visible. So what are you able to see in the Google Meet, uh, you know, web page or
I am using with
mobile?
mobile.
Okay. So what are you able to see? Are you able to see my screen? Is my video visible to you?
Your screen is. I am seeing your screen.
Sorry. Can you repeat? I couldn't hear you. Hello.
Hello. Yes,
Yeah.
sir. Whatever I thought, I am not seeing that thing. What I have seen, I am seeing your front page.
I will once stop sharing and then start sharing again. Let's see if you are able to view it then. Okay.
Yes, sir.
What about now? Is it visible now?
For me, it's okay.
Okay. Uh, Neeraj Kumar, are you able to view the slides now? Okay, I will take silence as a yes and move on for now. If there are any issues, we'll deal with them moving on. Okay. So here is question number 4, and we had received one response. in favor of all of the above, that is option D. And if you look at the correct answer, that is indeed correct. So slender body with flow separation, without flow separation, is needed for the formation of our thermal boundary layer. High Reynolds number is a sufficiently high Reynolds number is required, and a sufficiently high Prandtl number as well is required for the formation of thermal boundary layer. So, which is why all of the above would be the correct answer. So, moving on, we move on to question number 5. So, question number 5 says Pecklet number is the product of which of the following two dimensionless numbers? Is it option A, Bond number and Fourier number? Is it option B, Reynolds number and Prandtl number? Is it C, Grashof number and Nusselt number? Or is it D, Nusselt number and Prandtl number? So basically what this question is asking is that Pecklet number is the product of two other dimensionless numbers A and B. So what are these A and B? You have to pick out the correct combination from the four options given below. We have received a response in favor of option B, Reynolds number and Prandtl number, and that is indeed correct. So we can write Pecklet number as the product of Reynolds number and Prandtl number. So what does Pecklet number tell us? Pecklet number is nothing but uh, the ratio of heat transferred due to convection and heat transfer due to conduction only. Sorry, by advection and by conduction only. Reynolds number is nothing but a dictation of the flow regime, whether it's laminar or turbulent. And Prandtl number, that is a property of the liquid, property of whichever fluid that we are considering. It could be a liquid or a gas. It's a material property of that particular fluid. Okay. So moving on, we will move on to question number 6 of today's session.
Sir, 1 minute.
Yes.
Debjit sir, I want to ask you,
Yes.
Pecklet number, as you told, it's a rate of advection upon rate of conduction.
Yeah.
And Nusselt number is something rate of convection upon rate of conduction at the wall.
Yeah, they are similar in that sense, but their advection is not the issue with Nusselt number, that is convection as a whole. The meaning is similar, but not exactly the same.
But if you are going for Stanton number, it is Nusselt number upon something Pecklet number, no?
Standard number. I don't recall correctly right now, I'm sorry, but yeah.
So there is little confusion between then Nusselt and Pecklet.
Okay, then we will, focus some part of the next class on differentiating between these. I'm not well informed right now. I will dive down a bit deep into it and we will have a better discussion. Is that okay?
Oh, yes, yes. You got my question, na? It's
Yeah, that
Nusselt number,
seems
Pecklet
that
number,
multiple
and
numbers are representative of the ratio of heat transferred by convection and conduction. So, what is the difference between them? Why are we using multiple numbers? We could use only one single number only, right?
yes, yes, yes. Because Reynolds number and Pecklet, Reynolds number and Prandtl number,
Hmm.
it's actually derived number, just like that Pecklet number.
Correct.
And the standard number is also a derived number, that is Nusselt upon Pecklet number, that is REPR product. So why there is necessity to define this again? Already we are doing dimensional analysis,
Mhm.
and from number again we are finding out another number.
Yeah.
What is the necessity? And
What is
if
the
both are
necessity?
taking the same,
Hmm.
what is the use of it?
Okay. I'm noting it down and surely we will have a deeper discussion on it later. Okay. Okay. So moving on, we'll move on to question number 6 of today's session. So normal pressure gradient is comparable to axial pressure gradient while deriving the boundary layer equations. Is this statement true or is it false? So what I mean to say here is that there is a boundary layer and there is a pressure field all over. So these are my axis y and x. and there is a pressure field. So there is an axial pressure gradient, and I'm taking x-axis as my uh, you know the flow axis. So the axial pressure gradient would be dou p dou x, and there is a normal pressure gradient. So y is my normal axis over here. So there is a dou p dou y in this direction. So what I'm asking is whether the normal pressure gradient is comparable to the axial pressure gradient. So is dou p dou x comparable to dou p dou y in magnitude while deriving the boundary layer equations?
It is false statement, sir.
It
It's
is
not comparable because
correct.
delta p by delta y is zero.
Hmm, correct. So what usually happens is if we go here, so dou p dou x is actually much greater than the dou p dou y. We obtain this from scale analysis, and I hope everything is clear regarding this. So we will move on to the next question. Okay, so this is a numerical type question. So consider steady parallel flow of air. The properties of air are given, density and viscosity, over two parallel flat plates separated by a distance of 3 millimeter. The air has a temperature and free stream velocity of 300 Kelvin and 25 meters per second. Find the distance in millimeter from the leading edge at which boundary layer merger would occur. So if I draw a figure representing this, so there are two different flat plates. They are separated by a distance of 3 millimeter. I'm saying that there is a flow of air towards it. And draw a center line in between the two flat plates. And what will happen is there will be a growth of a boundary layer from this flat plate as well as from this flat plate. And as a result, uh, a little distance down the line, so we will call this distance, small l. There will be a boundary layer merger from the two different flat plates. So the question is to find out this length l. And a hint is given that you can use delta over x equal to 5 divided by root over rex. This is nothing but the Blasius solution of the boundary layer. Here we can use the solution itself to figure out this numerical, to find out the length at which boundary layer merger would occur.
Here delta we need to put 1.5 mm. Am I right?
Correct.
Because it is a fully developed flow at that point.
Hmm.
Sir, what is the characteristic length in this case?
Uh, Here, the distance small l only you can take as the characteristic length.
Small l.
The length at which the boundary layer merger occurs, or the development length, or the entry length, uh, which is that is the term we use for flow entering into confinements like pipes or ducts or something like that. So this is a similar problem.
No, actually, where I stuck in finding out Renault number at a distance x. So
Yes,
in Renault, it is
use x
VLC.
only over there and solve for that x.
No, Renault number is VLC by nu. So I know velocity,
Hmm.
I know nu.
Hmm.
What should be my characteristic length? That's the problem.
Yeah, take that as small l, and there is another small l on the left hand side as well. Then we can solve for that small l, right?
Okay, okay. On both side it
On
is.
both sides it is the same.
Yes.
Could you land into the solution, sir?
No, sir, no, sir. I think I'm missing some calculations here.
Okay. Okay, let's have a look at it. So the correct answer is 141 millimeter, and we will look into how to find that. So basically, this equation is already given, delta by x. X here we will write as L, that is the length at which boundary layer merger occurs, and 5 by root over REL. So 5, I hope you don't mind if I write it as, you know, U infinity into L by nu. Fine?
Yes, yes, I got answer, sir.
Okay. So from now, if I take L on that side, L to the power minus half would be equal, and okay, so here we will replace certain things. We will put 1.5 millimeter in place of delta, and in place of U infinity, we will put this as 25. Okay, let me do this properly. So delta by L equal to 5 by root over U L by nu. If we rearrange it a little bit, so this would become 5 root over nu by u into L. Now I'm moving on over here for space. So this L I'm taking on the left hand side. So L becomes L to the power minus half, and delta would be equal to 0.0015. So this should be equal to 5 into root under nu. So nu is 15.89 into 10 to the power minus 6, and this would be divided by u, which is 25. So root under 25 would be 5, and we have 5 outside, so these two get cancelled, and 15.89 we can roughly take that to be equal to 16, so we can write this roughly to be equal to 14 into 10 to the power minus 3, and now, if we take this 1.5 millimeter in the denominator, so I'll write L to the power minus half equal to 4 into 10 to the power minus 3 divided by 1.5 into 10 to the power minus 3. So these two get cancelled, and we will keep it like this for now. So if we now solve for L, so we take a power of -2 on both sides. So that would mean this would become L, and this would become 1.5 by 4 because of the minus, and we will take a square of that. So if we solve it, this becomes 0.375 square. And if we calculate this, this roughly becomes something around, 1.41 millimeters. So this would be initially 0.141 meters. If we convert it to millimeters, roughly this would be the value. Is the solution method clear?
Yes, got it. Actually, I have not converted that mm into meter. That's the issue.
Oh, okay.
Yes,
The units are very important. Okay, so another numerical. So over here we have for flow of fluid over a heated plate, the following fluid properties are known. Density is known, kinematic viscosity is known, specific heat at constant pressure is known, the thermal conductivity is also given. So given all this data, the hydrodynamic boundary layer thickness at a specified location on the plate is 1 millimeter. For some value of x, the delta is 1 millimeter. The thermal boundary layer thickness at the same location is how much, and we have to find this in millimeter. So a particular x is given, delta at that is given, we have to find out the delta t over there. So if I draw an accompanying figure to this, there is a flat plate like this. It is at a certain temperature T, and there is an incoming flow with U infinity and T infinity. We have a formation of a velocity boundary layer or a hydrodynamic boundary layer as well as a thermal boundary layer. It could be bigger than the hydrodynamic boundary layer also. For the sake of an example, I'm taking it to be smaller than that. So this is delta and this is delta T. The hydrodynamic boundary layer or HBL and a thermal boundary layer or TBL. So what the question says that there is a particular location, a certain x, so to say, x comma 0. So here I know the hydrodynamic boundary layer thickness delta, but at the same location what would be the thermal boundary layer thickness? This is the question. At different conditions of flow as well as the flow properties, they are given. We have to find it out.
Here we need to calculate Prandtl number.
Yeah. All the properties are given. Prandtl number can be calculated from there.
Prandtl number comes at 0.16 something.
So that means Prandtl number is lesser than 1. And
This
Prandtl
delta is
number,
less than delta T.
yeah, Delta is less than delta t, correct. So for that situation, what would be the relationship determining delta t along with Prandtl number? We'll have to use that.
No idea, sir, about it.
Okay, let's look at the correct solution is 2.5, and we will have a look at the solution how to do it. So the thing is, we know that delta by delta t is equal to Prandtl number to the power minus m. Now this m is different for different situations. M is equal to half if uh, Prandtl number is less than 1, and m equal to 1/3 if Prandtl number is greater than 1. So they respectively mean something else, like delta being greater than delta t. And did I do this correctly? Prandtl number less than 1. Prandtl number less than 1 means the momentum diffusivity is less. Yeah. So delta t would be greater than delta over here, and Prandtl number greater than 1 means delta would be greater than delta t. Okay. So first of all, we have to find out the Prandtl number. So Prandtl number, if we try to find out, Prandtl number is nothing but the momentum diffusivity over thermal diffusivity. Momentum diffusivity or kinematic viscosity, that is already given, and alpha we have to calculate. If we separately try to calculate alpha, alpha is equal to, sorry, alpha is equal to k over rho cp. K is given, how much is k? K is given as 5, rho is 0.25, and cp is 1.6 kilojoules. So we have to convert it to joules, so it would become 1600. Now if we try to do this, we will remove this decimal instead of these two zeros, and 5 would divide 25 to give 0, so this would be around 1 by 80. If we put this over here, 1 by 80, so 1 into 80. So Prandtl number becomes 0.16. Up to here you could reach, right? So here we see
Yes.
this is less than 1. So as a result, m would be equal to half. So that gives us that del by delta t is equal to Prandtl number to the power minus half. And Prandtl number we have already found out to be 0.16. So 0.16 to the power minus half. This becomes 0.4 and 1 by zero point 0.4. So this becomes 1 by zero point 0.4, which is equal to, I guess, 1 by zero point 0.4 means 2.5, right? Yeah,
Yes.
2.5. So delta would be equal to, okay, now delta t we have to find out. Sorry, am I messing up something? Delta by delta t would be equal to,
Point 0.4, I think.
let me find the number now. This is correct.
Actually, it is getting reversed.
Yeah, that is what I'm thinking. So minus sign would not be here, I guess. Prandtl number is, okay, so this is proportional to delta. Okay, sorry. So delta over delta t is Prandtl number to the power n. So usually what is written in books is delta t over delta is Prandtl number to the power minus n. So this is where I messed up. Okay. So I'll try to remove all this. Okay.
Answer is simply reverse 2.5 mm then.
Yeah, correct. So delta t by delta, this is equal to Prandtl number to the power minus half. Prandtl number we already know to be 0.16 to the power minus half. And this would be 0.4, 1 by 0.4, which means 2.5. And delta we already know is 1 millimeter. So delta T would be nothing but 2.5 millimeter. So as a result, option B would be the correct one. Okay. Sorry, I messed up a little bit in between. Is there any questions regarding this?
No. It's m is equal to 1 by 3 when Prandtl number is greater than 1.
Greater than one, yeah. Which is true for low conducting fluids with high viscosity. That is for heavy oils and any normal fluid like air or water or so on. For air, I guess it's 0.7, but for water it is more than one. And other fluids which are of engineering interest, they are also more than one. It's
That
less.
is practically a rare case.
Yeah. Correct. Okay. So we will move on now. We will move on to question number 9 of today's session. So this is again a theoretical one. So the conditions for a Stokesian fluid or a Stokesian fluid is option A. The relationship between stress and rate of strain is linear. The volumetric strain rate is 0. The fluid is homogeneous and isotropic, or is it D, none of the above? So there are a set of conditions which qualifies a fluid as a Stokesian fluid. Which one is that among these four options?
Homogeneous and isotropic.
Correct. So if it's homogeneous and isotropic, then it qualifies as a Stokesian fluid. What about the others? The option one, what is it?
Newtonian. Newtonian.
Newtonian. And if the volumetric strain rate is 0,
No, sir.
then it's an incompressible fluid. So what does volumetric strain rate mean? It's basically dou u by dou x, dou v by dou y, and dou w by dou z. So they basically mean that if I take a fluid element and if this is dou x, whether this is whether the velocity at this point and this point, whether it's changing with dou x or not. If it's changing, then over a course of time it would elongate this way, and if this is equal to 0, then there won't be this elongation or compression for the other way, vice versa. So if this linear or this volumetric strain rate, if it's 0, then it means it's an incompressible fluid. Okay.
Yes.
So moving on, this is the last question of today's session. Which of the following non-dimensional group is not present in non-dimensional form of the energy equation? Is it option A, Nusselt number, B, Eckart number, C, Reynolds number, or D, Prandtl number?
What I guess is Eckart number probably.
Okay, no, it's the Nusselt number which does not appear. So we can have a look at it. So we will, simply do something. We will take a one-dimensional unsteady heat energy equation and then try to non-dimensionalize it. So if we try to write that, it's rho Cp dou T plus we will take only u dou T dou x. Now I hope you understand that for more dimensions we can take others also, like v dou T dou v and v dou T dou y and so on. I don't want to make this messy, so I'm keeping it down to one dimension only. And here we would have the capital dt, that is material derivative of pressure. So here we will break it down and write it as dou p dou t plus dou p u dou p dou x. This is the pressure part, and there would be a conduction part, sorry, that would be dou t dou x square. Since we are keeping it down to one dimension, there won't be more. And apart from that, there will be this dissipation term as well. For general flows, this does not become much important, so we will drop it here, and we will try to non-dimensionalize the less of it, the remaining part of it, what is left. So we'll define some scales. So x star would be x by L. This is how we will non-dimensionalize it. So u would be u by u infinity, u star would be u by u infinity, and non-dimensional temperature theta, theta we will define as T minus T infinity divided by TW minus T infinity. And what else? We have pressure. Pressure we will do it as pressure, non-dimensional pressure would be pressure by the stagnation pressure, whatever, rho u infinity square. And time we will non-dimensionalize as time divided by some time scale. We will take this as L by u infinity. Okay, so if we now plug them in over here, so we have rho into Cp on this side, dou t. So what would be dou t? From here, if we did dou t, okay, there is no space here. I'm trying to write them down over here. Okay, we will use them in the equation. So if I try to differentiate this, this becomes dou theta equal to dou t divided by tw minus t infinity. Similarly for others also. So let's say dou x star would be x by dou x by L. So dou x would be L into dou x star, like that. Similarly, dou u star would be dou u by u infinity. And similarly others also. I'm not writing down everything. So here if we replace this, dou t would be replaced by dou tw minus t infinity into dou theta, and time would be time derivative dou t, that would be L by u infinity dou t star, L by u infinity dou t star. Similarly here the u scale we will simply, okay, there is simply u, so we will replace that with u infinity into u star. Dou t, similar thing that we did earlier. For dou x, it would be L into dou x star. So that takes care of our left hand side. This side, okay. Now dou p dou t. So here what we have, dou p would be rho u infinity square dou p star, and by dou t, so that would be L by u infinity into dou t star. Similar to that, we will replace u as well as dou p with dou p star, and in place of dou x, we will have L dou x star. So this is for the pressure term. For the conduction term, there will be K as usual in front, and in place of dou t, there we will have T infinity Tw minus T infinity dou 2t divided by, what do we have here, dou x square. So we will take a square of that, L square and dou x star square. Okay, so this is the equation which we have right now. We will try to clean it up a little bit. So let's say we are deleting this tw minus t infinity from, sorry, this we are deleting from everywhere, but since this term doesn't have it, we will have a 1 by Tw minus T infinity over here. Up next, we have this U infinity common in the numerator. So this U infinity, if we take it up, it will be in the numerator. So this we are deleting from everywhere. And since this last term does not have that, it will come in the denominator over here. Okay. Anything else? We can take L out from the denominator as well. So all of these have at least one L, so they go out the window. And what else? Okay, rho CP. Rho CP I am taking out from, okay, rho CP we will send in the right hand side later. Okay, I'll move on to the next page for this. It's getting too clumsy. I'll write it down once again. So this time I will take rho CP in the next page. So, sorry, in the right hand side. So I will not write it down there. I will simply write dou theta dou T star plus U star dou theta dou X star equal to, okay, so in front of the pressure term we have, okay, I forgot to delete L from here, so this L was also deleted. So in front of the pressure term we have rho U infinity square. In front of the pressure term we have rho U infinity square, and from that side we are bringing down rho Cp, and there was one by T to the power T infinity, this temperature difference also, so that also we will keep here. So that would be in the denominator, and that's all. Then we have, in between we have this pressure material derivative, or a material derivative of pressure, plus in front of these, in this diffusion term, here we have k, k in the numerator, and in the denominator we have L and a U infinity. L and a U infinity, and from that side we are bringing in rho Cp. From that side we are also bringing in rho Cp. Here we have nothing but the diffusion term. Sorry. Okay, so now we will try to arrange things down a little bit. So rho gets cancelled, and this, as we know, this is nothing but 1 by Eckhart number into the material derivative of pressure and this second term we will try to resolve them a little bit. This k divided by rho Cp, what is it? This is something that we know. What is it?
Which one, sir? This one.
The k by rho Cp,
Alpha.
alpha.
Thermal diffusivity.
Correct. So we have alpha over here, and this L by U infinity is in the denominator. So here what we will do is we will take the kinematic viscosity, we will multiply it once and divide it once. So this becomes the 1 by Prandtl number, and this becomes 1 by Reynolds number. So essentially it boils down to 1 by Eckhart number over here. We have the, I'm not writing the entire thing once again. This is the material derivative of pressure plus 1 by Reynolds number into Prandtl's number into the diffusion term. I forgot to write it here. So we saw how to non-dimensionalize the equation. So,
I have to see, I think, twice these slides. When you upload the video, I will do it.
okay. So this is how we saw how to non-dimensionalize this, and we are seeing that the non-dimensional numbers which appear here are the Eckert number, the Reynolds number, and the Prandtl number. Nusselt number doesn't show up anywhere over here. Okay.
Yes.
That's why the correct answer would be option A.
Are you going to upload this video, sir?
Yes, sir. Last week also I uploaded. Can you see it in the NPTEL webpage?
No, I haven't checked it. The reason is actually I understood everything last time. Now for this last session, I have to repeat the video.
Okay.
At least
If you
this
have
question.
any questions, we can have further discussions also. No.
Just a small question.
Yeah.
If I know temperature profile, how to calculate the Nusselt number? If I know the equation of temperature profile, it's a non-dimensional temperature gradient. Am I right?
Yeah.
Nusselt number. So if I know temperature profile equation,
Yeah. How to
fix it?
Okay. So there what we do is, how Nusselt number is written is, so we can write this as, okay, one thing is the conduction through a film is equal to the convection over there. So K
So it is
dou T dou Y should be equal to H into whatever delta T that is there. So if we, and dy can be written as a length scale. So K, so if you take these two over there, so HL by K, that becomes the Nusselt number. So this dt dy, that is something that we know if we know the temperature profile, right?
we can differentiate it, no?
Yeah. So HL by K, this basically becomes H by L. K is something that we know, and H can be written as K by delta T into dou T dou Y, and there in the denominator as well, and there is some length scale as well. Length scale of the problem that we know.
Just 1 minute, sir. What is this step? K by delta T, how it comes? K
This is
by...
nothing but H, which I calculate from
Yes,
here.
yes.
And this is the length scale of the problem. This is the thermal conductivity. K you can cancel over here, and this is what remains.
No change. She went to the grocery store next door. So it is L by delta T, delta T by delta Y.
Yeah. Okay.
Okay.
So that's all. We will end the session today over here, and we will have another discussion next week.